Okay, everyone. So thanks a lot for joining. Welcome, everyone. I think we'll kick off. Sure, a few more people will jump on, but yeah, welcome to our third Eliiza virtual brown bag. I'm Graham Spence, a data scientist here at Eliiza. So this series of talks is wanting to cover a range of data science and machine learning topics, hoping to stimulate ideas, share knowledge, and yeah, and really importantly, stay connected at this time that we're in. So yeah, everyone who's registered will receive updates on future talks. Please, as I always say, please feel free to forward, share the invites. Yeah, really keen to yeah, keep this going and keep connected, and as I said, share knowledge. Just before I hand over to Tim, I'll just go through a couple of ground rules, as we always say. Please just stay on mute so that we don't have background noise, and turn your videos off. I think everyone's done that just to keep the bandwidth down. If you have any questions, please submit them in the chat feature. And yeah, like last time, we're open to unmuting and doing the questions directly so that we can clarify and have a bit of discussion afterwards. And today's session will be recorded and published on the Eliiza YouTube channel. And we'll email out the slides and link to the video. So yeah, hopefully the talk will inspire some of you to look at opportunities to do advanced machine learning in your organizations, and if you're keen, we can help. This is a general email address. I know Tim will give his email address, and we'll have a follow-up information in the email today or tomorrow. So great, I'm just going to hand over to Tim, a machine learning engineer at Eliiza, to talk us through this talk. Thanks, Tim.
Thanks, Graham, and thanks everyone for coming. So my name's Tim. I'm a machine learning engineer with Eliiza, and today I'm going to be talking about testing in machine learning. I'm going to start out by talking about two kinds of software, a model popularized by Andrej Karpathy. The first kind on the left is called 1.0. It consists of explicit instructions in a language like Python or C++, and it's written by a programmer. With each line of code, a programmer defines some known desirable behavior at a specific point in the space of possible programs. I'm going to call this sort of work 1.0 programming. The second kind of software is called 2.0. It's written in this abstract, human-unfriendly language like the weights of a neural network. No human is involved in writing this code. Instead, we specify some goal on the behavior of a desirable program. For example, satisfy a data set of input-output pairs of examples. We then write a rough skeleton of code, like a neural network architecture, that identifies a subset of program space to search. And then we use the compute resources at our disposal to search this space for a program that works, using processes like backpropagation and gradient descent. I'll call work in this stack 2.0 programming. And it won't be any surprise to you that it turns out that an increasing proportion of real-world problems have this property that it's significantly easier to do things in the 2.0 stack than the 1.0 stack. That is, it's easier to collect data to identify desirable behavior than to explicitly write a program. For these sorts of applications, you then got two sorts of programming work. The 2.0 programmers curate, clean, and label data sets, which are used to program the final system. The 1.0 programmers maintain the surrounding tools, analytics, visualizations, and infrastructure. Adding the 2.0 stack changes programming in the following ways. First, there's different team skills. In a 2.0 project, the team usually includes data scientists who focus on exploratory data analysis, model development, and experimentation, and who might not be experienced software engineers. Additionally, it's experimental in nature. You try different features, algorithms, and parameter configurations, and you need to keep track of what worked, what didn't, and still maintain reproducibility. Furthermore, testing is more involved because on top of your code, you're now also testing your data and your models. And deployment is more complex because it can require you to deploy not just a model, but a multi-step retraining pipeline. Finally, software can have bad performance, not just because you wrote some bad code, but also because of constantly evolving data profiles. And when we work through these complexities, we end up in this world of machine learning applications where only a small amount of the total code and components is actually directly about the machine learning part. So there's obviously still a lot of overlap between how we develop software here and how we do it if there was no machine learning involved. A response to the challenges posed by adding the 2.0 stack to programming is to apply a continuous delivery approach to machine learning, which is often called ML operations or MLOps. MLOps is about making machine learning programs reproducible, testable, auditable, and continuously improving. So far in this presentation, I've just looked at this broader context so you can see what's motivating the rest of it. In the rest of the presentation, I'm going to focus on one part of the MLOps framework, which is testing. And I'll try and suggest some answers to the question of how do we bring good testing practices to the new stack and make sure we're building quality software. The content from here on in is mostly going to be aimed at people with a data science background who don't necessarily have much software engineering experience. And it's mostly going to be musings, ideas, and code snippets from my own misadventures doing testing and machine learning. So I hope you get something out of it. And if you have any feedback, I'd love to hear from you. Before we start, I'm going to flag some things we'll need to overcome when doing testing in the machine learning world. First, some things are computationally expensive to test. So think model training and data transformations on large feature sets. Additionally, models are created via non-deterministic processes. So it's difficult to craft focused assertions about what their outputs should be. For example, you can train two models with the same training data and the same algorithm, which end up having different output predictions for the same input data. Lastly, and perhaps most obviously for a lot of data scientists, a lot of the work you'll do in the initial phases of a data science project is experimental. As I'll argue, this one really comes down to what you mean by testing, which is something I want to challenge. You've probably heard of test-driven development before, where as much as possible, a developer writes tests first and then tries to write code which passes those tests. There's some empirical evidence about this approach. In a study run by Microsoft across a bunch of development teams, software built using TDD took 15 to 35% more time in development. But it also reduced bugs by 60 to 90%. And we know that everyone writes bugs, but everyone writes bugs, especially in machine learning. That's because there's at least 4 extra dimensions where things can go wrong, which creates this combinatorial explosion when you're trying to debug your code and figuring out where the problems are. Those dimensions are data issues. For example, not enough data, weak labels on your data, or data drift over time. Implementation correctness, so think like incorrect gradient computation or incorrect feature creation. You've got model issues, for example, like non-optimal regularization or over and underfitting. And lastly, there's like the correctness of your training algorithm, so think poor or suboptimal learning rates. And it's important not to forget the other reasons why testing is good, namely, you're going to be more confident that your code works, your code won't break easily upon changes, your code can be refactored simply, and your code can be extended without breaking the rest of it. So I'm going to reframe the test-driven development concept a bit and call it test-driven machine learning. And I'm going to suggest some ways you can use some of these concepts we've been talking about to create better machine learning applications. First, let's talk about some similarities in the approach. Data science is trial and error. You generate a hypothesis. For example, this modeling approach can distinguish cats and dogs with 90% accuracy. You test that hypothesis and you rinse and repeat. Test-driven development follows the same logic. A test is a hypothesis about your code's behavior, which you then seek to go out and validate. In this view, evaluating your model's performance is just another kind of test. And things like data augmentations are also a kind of test, where you might deliberately add synthetic training and validation data to ensure your model behaves correctly for a range of different data inputs. Tests can also serve as a way to document your behavior, to document your assumptions about the behavior of your code, as well as your data and models. Tests allow us to write these assumptions once, and from then on, we can easily retest those assumptions and see if anything we've written has broken them. This approach also leaves room for experiments. We can check for things that might not ever work. For example, we can test if our model performance ever gets way above an expected threshold. So let's start to operationalize this concept. On a machine learning project, you're going to write some code. Some code will be for working with your data. Some code will be for your training procedure. Some code will be for serving your model up in production. And a lot of code will be for other stuff. With the exception of code, you might write an exploratory data analysis and potentially some other exercises. For an enterprise machine learning project, all code should be tested. And your training code is also production code. That last point is probably made a bit clearer by this diagram, which is part of Google's MLOps maturity analysis. This depicts a relatively mature machine learning environment. On the top half above the dotted line, we have our experimentation zone, where a data scientist produces a model via some procedure. This procedure, which we'll call a pipeline, is encapsulated within this top blue box. And it consists of tasks like data validation, preparation, model training, evaluation, and validation. In a robust deployment environment, this same pipeline code is going to be used later down in our operational zone below the dotted line. It's used later because it allows us to automatically retrain models based on things like performance drift, new data availability, or new changes to some of our pipeline code. So any code you write during this experimentation phase at the top is hopefully going to make its way into production, which means we need to test it. Which begs the question, what should we test? Well, first, we want to test our data against an expected schema. For example, are values falling within normal ranges, like numeric features scaled and normalized properly? Does the data take expected values? For example, are we handling null values correctly? The second area is we want to test integration between components. For example, can our model's API be consumed by the services which need to talk to it? Or when we export the model to a different format, does it still produce the same results? A third area is in validating model quality. While ML model performance is non-deterministic to an extent, we still routinely use a number of metrics to evaluate performance: error rates, confusion matrices, error under the curve, precision and recall, etc. We can use these metrics to establish performance requirements and ensure that new models don't degrade against a known performance baseline. And lastly, we want to validate model bias and fairness. For example, you may have inherent bias in your training data, where there are many more data points for a given protected attribute, like race, gender, or religion, compared to the actual distribution in the real world. Additionally, if your model is making predictions about people or something important, we want to ensure that those predictions meet the criteria of fairness that we've chosen. I'm now going to talk about a couple of useful ingredients for testing your machine learning code, and then I'll go into some testing heuristics. I'll be using Python as my example language, so apologies to any non-Python users here. The first useful ingredient are called mocks. Mocks allow us to replace dependencies with objects that simulate the behavior of real ones. A useful Python library for doing this is called, unsurprisingly, mock. One way to use this is to mimic the behavior of external cloud services, so we don't need to have an active connection to the relevant cloud service when we're running our unit tests, as we're not testing those services, but our code. In this code snippet, here at the top, I've got a function called upload_model, which is responsible for uploading a trained model into Google Cloud Storage using their Python SDK. When it comes to testing functions, which use this upload method, for example, at the bottom, we can use mock to patch the storage connection, which is what I've done here. With this mock.patch decorator, we can run our code as normal, which in this case trains and uploads a model, but without requiring any connection to Google Cloud Storage. For testing purposes, we can directly check our fake mock object, whether it was called with the correct arguments, in this case, the name of the model being uploaded. Another good example of using mocks is in data pipelines, where you're mocking a CSV read operation, for example. So we don't have to read in the large table, but you can instead use a mocked CSV dataset object throughout our pipeline code. The second useful test ingredient I'll touch on are called fixtures. These are like little utilities that allow us to set up a well-known and fixed environment to test against. In machine learning, we don't want to clog up our code repo with a bunch of training data just for testing purposes. So one way we can use fixtures is to automatically create training data on the fly based on different parameters that we want to test. This is a relatively simple example which shows a training data fixture for a regression model. Here I'm using the PyTest library to create the fixture. We pass it the number of training samples we want, the fraction of those to be used for validation, and the data range across which we want our numeric features to vary over. We then get back a way to directly make a training data set on the fly, which can be small or large with different sorts of values, which you can use in our various tests. I'll show this fixture in action in a later example. Now that we've got a sense of what we should test and a couple of key ingredients, here's a list of heuristics that I think are useful for how to test these things. The first I'll touch on is the old and faithful unit test. This is the atomic level of testing, where we're isolating single functions and testing their behavior with different inputs. Ideally, we want to write unit tests for each novel function in our code. Here's a nice and simple example to get us started. In this example, I'm unit testing a transformation on a data frame, which is creating a new feature for me. Our input data frame, which is called robots, tracks a number of naughty robots over time. Our transformation, which we're importing here, is called add_change, and it creates a new column in this data frame called change in naughty robots, which is our new feature, tracking the change in naughty robots between different time steps. So for this test, on top of our input data frame, we created an expected output data frame, run our add_change function over it, and ensure that the output matches what we expect. Note that I haven't actually defined the add_change function here, and I didn't need to. I knew what I wanted the function to do, so I wrote a test to check for that behavior. Our second test heuristic is called a threshold test. This sort of test monitors some measurable phenomenon like model accuracy by comparing the value in the current build against some threshold value. In the case that the current build's value passes the threshold, the test fails, breaking the build and preventing deployment or merging. Here's an example of some threshold tests which monitor our model performance. In this case, our training pipeline has output a metrics file into a results folder. After our training pipeline has executed, we can run these two tests. The first checks two things, the normalized weighted root mean squared logarithmic error and the R² values, both against our predefined thresholds. The second test looks at the model's fairness across its predictions using a score called demographic parity, which seeks to ensure that protected classes receive positive outcomes at equal rates. The choice of both of these sorts of metrics is obviously extremely important and is going to vary a lot depending on your use case. Another very common test heuristic which I'd like to touch on is integration testing. This tests whether the different modules you've written work when you bring them together as a unified solution. For example, your UI is able to integrate with your model, or that the different stages of your training pipeline will fit together. When training a model as part of this process, in order to ensure deterministic behavior, and this goes for other sorts of tests in general, you can use methods like TensorFlow's setSeed, which makes sure that stochastic processes being run during training use the same values. In this simple example, I'm using the training data generator fixture I showed earlier, which I can use as an argument to my test. This argument is actually a function, which I can call to generate training data. In this case, with 40 training samples, 25% of my data going to the validation set, and my numeric features ranging between 0 and 100. I then pass that data to a training pipeline, which passes me back a model, which I then test to ensure it can run predictions and produce the expected sorts of output. This is testing that our various training pipeline steps have resulted in the data set, which is able to train a model, and that the ensuing model has part of the interface that we expect. We would also expect unit tests at each step of our training pipeline as necessary. And here's a bunch of other ways to test ML code, which I won't go into in detail, but I'm sure a lot of you will have familiarity with. There's contract testing, which is making sure your test doubles, for example, mocks, match the actual services you're communicating with. There's seam testing, which is a method of testing legacy code at points of integration. There's load testing, which allows you to simulate your deployed software under heavy usage conditions. There's cross-validation and learning curves to address over and under fitting. There's adversarial testing and specification fitting to address the robustness of your models. That is their ability to handle strange and wonderful cases not seen during the training regime. And lastly, for now, there's measures like the Wasserstein distance, which is a way of measuring the statistical difference between the data you're seeing in production and the data you saw in training in order to measure data or concept drift. And here's a wonderful and beautiful testing pyramid for machine learning applications, which sort of works at trying to pull these all together. You can see we've got some of the key elements which make up our machine learning system, being the data, the model, and the serving layer. And each of these components have their own set of unit tests, validation, and integration points, where we test the interfaces between them, all leading up to a final set of integration tests across our entire application stack. So I'm going to wrap this up as a nice step-by-step. First, we're going to set up a test framework. So choose our libraries and any initial fixtures and mocks we know we'll need. Second, we set up a test pipeline using a tool like Jenkins, Bamboo, or GitHub Actions. We can then define merge conditions on our repo. For example, only merge into a set branch and or trigger a deployment if our desired tests pass. Third, we define the set of things we want to test, which we'll call happy cases and sad cases. Happy cases are things like getting regular expected training data, the model successfully trains, or the predictions are fair according to our metrics. Sad cases are when we've got unstable data, the model doesn't train correctly, some other edge case occurs, or our output is biased. Fourth, we define what we want our code to do in each case, and then we write some tests for that behavior. Finally, we write more tests when we change our opinions about what our application should do, or when we find a bug. Before we start opening things up for any questions you might have, I'll just go through some extra quick suggestions I found useful. As a starting point in Python, I definitely recommend using PyTest. You can really easily get going with testing with very little overhead. I'd also recommend exploring using lots of fixtures in your tests. These end up making it a lot easier to write new tests with less code. Along those lines, to keep things lightweight and easily parameterizable, try and keep your test data inside your code as opposed to living as files inside your repo. The training data generator I showed before is an example of that. A general testing trap, which it's easy to fall into, is testing implementation details as opposed to the inputs and outputs of your code. An example of this is testing that some class attribute takes a particular value, which is only used in the course of generating some of that output. Only testing function interfaces makes it easy to change implementations and not break your test. Some common packages also have their own inbuilt test libraries with their own helpers and fixtures you can use. A good example of this is TensorFlow with their tf.test.test case, which sets up an environment for you embodying a TensorFlow session, so you don't need to worry about those details yourself. And lastly, a big thing which I haven't touched on is running experiments and experiment tracking. This is a big topic all of its own, but for now, I'd recommend checking out the open source tools DVC, which stands for Data Science Version Control, as well as MLflow. And finally, here's a good list of resources I've found on this topic and related topics. If you'd like to get in contact about any of the content here or get a copy of anything in these slides, just hit me up on my email shown at the bottom. Thanks very much, everyone, and I'll now move on to take any questions you've got.
Cool, thanks, Tim. I'll just give people opportunity and time to think of questions or write them in chat. I've got a question. I just wondered if you could elaborate a little bit more on your point on the previous slide in terms of where possible keep data in code, and just how you would approach a problem where it'd be quite tricky to create realistic random data and sort of whether you could or should use a realistic subset of your real data in a testing process.
Yeah, that's a good one. So you can get pretty tricky with this. I'll go back to my code snippet that I had on this. Yeah. So this shows a fixture where we're automatically generating a bunch of training data. And so this is like a relatively simple thing. We're just passing in like a basic data range, but you can actually sort of, for each feature that you're automatically generating with this, you can set values, as you mentioned, by deriving them from some sort of statistical range across your actual data, or you can define probability distributions yourself to test things that you might not even find in your input data. So it really depends on the sort of data that you have. If you're if you're using images, for example, this gets a bit tricky. But for columnar data and sort of categorical data, numerical data, it's pretty easy to create these generators where you can really reason about what sort of values you expect and play with the different ranges that you want to vary those across.
Yeah, cool, thanks. Cool, I think there's a question in the comments.
Sorry, did you want to read it out?
Yeah, sure. So, so Michael has said, at what scale of application machine learning activity do you believe that the different test heuristics should be applied? Is there a kind of bare bones expectation that is best practice? And yeah, well, obviously Tim can answer, and Michael, you can feel free to unmute and follow up anything.
Yeah, so I'm assuming by scale you're talking about like whether like it's sort of a home sort of test project you're doing, or maybe like a project with a company or something like that. In general, I think tests, like I hate writing tests, and tests are often scary, but they end up being useful for a bunch of different things. And for the projects that sort of I write and do in my own time, it's really difficult to add tests to them and really annoying. But if I know that I'm going to be working on something for a long time, it's definitely worth doing. And depending on, this is a good sort of example of sort of what sort of, this pyramid is a good example of the different sort of tests you want to involve depending on what components you're actually writing as part of your projects. But it's just this really good way of, one, writing down your assumptions, and two, making sure that things don't break later on when you make changes in unexpected ways. Feel free to chime in if that didn't answer the question, by the way.
Cool. Yeah, I mean, that's sort of one of the questions I was going to have as well, just whether you need to have a sort of a specific defined tipping point from some exploratory work to sort of if it's a product development or productionizing a model. But yeah, obviously it's a case-by-case basis. Do you have any examples or ideas, Tim, of when that tipping point is, or is that sort of data scientist dependent as well?
Yeah, this is a tricky one that you know, we come back to a lot. It's like, at what point do you start sort of pulling code, let's say, out of a Jupyter notebook and into like an IDE? Because it ends up being pretty hard to do testing in notebooks. If anyone's got a good testing solution for notebooks, I'd love to hear about it as well. But yeah, you'll find, you know, there's this obvious point where it doesn't make sense to do tests, which is where you're just exploring the data, doing some EDA. And then at some point, you're going to start writing like some sort of set of data transformations to do some feature engineering. And it's that point that you've really started writing your machine learning pipeline. And it's at that point that you really want to start thinking about tests. So for me, that's when I'd be like pulling code out of a notebook and putting it somewhere else. But obviously, everyone works differently. Everyone has familiarity with different tools. So it ends up being super fuzzy when you start doing that. Yeah, but I'd love to hear some good answers to that as well.
Yeah, great. So the question from Laura Summers here, she says, related to the point on random sort of synthetic data, she says, what are your thoughts on how to validate non-numeric data like speech, sound, images, and video?
Yeah, it's a good question. I suppose there's like common practice is to do like a range of like augmentations on the data. So you take your input data and then you add a bunch of extra training samples to it by perturbating it unexpected ways, like flipping images around and stuff like that. I'm actually not sure what the equivalent is for audio. I haven't really worked in that domain much. I know Hugh, who is on the line, has done a lot of work with audio stuff, so he might be able to chime in there. But yeah, I think like in general, a good practice is like thinking about what sort of data samples you're going to see in the real world that aren't represented in your data, and test that what you're producing like has some like your expected behavior when you pass those in. And then it's really up to the specific data structure how you apply those transformations yourself. Did you want to jump in about any audio stuff here, if you're there?
Can you hear me?
Yeah, man.
Sorry, I'm using different headphones and not sure if they work. I think it was someone else that did the forum talk on that. I haven't actually done audio stuff before.
Nice.
So sorry.
Yeah, that's cool. Yeah. Sorry, you did the Dan one. Yeah, cool. Any interesting ideas anyway?
And I also missed the question. So sorry to be
comments.
A troublemaker.
I suppose there's any properties you can derive from any audio, so sort of any sort of derivatives or noise or measures of that sort of thing, sort of stochastic features or sort of things, a bit like how you would look at means derived from a column of numbers. You could sort of think about, okay, what features can summarize obviously important properties for the data maybe.
Yeah.
We've got a really good question here, which hopefully can spark some thoughts and discussion from Hayden, saying, I'm interested in your perspectives on the roles involved across the breadth of content covered. Where is testing the jurisdiction of the data scientist versus machine learning engineer or another role?
Yeah, it's an interesting one. Yeah, and feel free, anyone else on the call, to chime in on this. I suppose in my experience, like often we work on cross-functional teams which have like a range of different roles represented. And I found like having a dedicated testing team or someone who's responsible for tests in data science especially doesn't really work, because in order to test something properly, you need to have like a good understanding of what the expected behavior is and what sort of properties the domain area and the data have that are interesting and relevant and could throw problems later on. And it turns out in data scientists that like those sort of that understanding and that knowledge is like what makes up sort of the skills of a data scientist. So I think, yeah, like the only way that you can really be sure that your application, or like be more confident your application is going to be work, is probably going to be writing the tests yourself. So I think like, yeah, in the end, it's a job for everyone. When you get up to like system integration level testing and like testing APIs against each other, like you're sort of getting out of the realm of the behavior of your particular data science implementation. And at that point, you know, it might be more of an engineering job. But at this like lower level of the pyramid that you can see here, I very much see that work, that sort of as the work of the person who's writing the data science code. Hopefully that answers the question.
Yeah, and it chimes exactly. Michael has added a comment saying, I think along those lines, saying the person who writes the code should write the test. They often know the edge cases of the function's behavior, and at least maybe it's a starting point. Yeah, so it's great. And so we've got a question from Patrick, and hopefully Patrick can unmute and ask directly so we can hear exactly what he would like to ask.
Yeah, so I thought this was interesting. To me, there's kind of two different versions of a test that you might want to run. Like there's a lot of tests are around verifying correctness of an implementation. You know, like a great example would be like I've written some code that does statistical inference, and I've got this probabilistically generated data. Can my model, can my statistical code estimate the underlying probabilities? But a lot of data is really messy, and I guess you kind of went into this a little bit, but writing tests for validating that your real world data matches some assumptions, and like using tests as a documentation of hypotheses rather than you know, you need all these tests to pass for CI/CD.
Yeah. Yeah, it's a good question. I suppose, yeah, there's like, I sort of want to merge these concepts together, because in the end, you've sort of got this very similar way of writing tests and this concept of a test pipeline, which has different stages. So at the start of a test pipeline, as you say, you'll sort of test, like you'll unit test your functions with sort of your known or synthetic data, sort of all the different aspects that go into like model training. Ensure that all works, and if that all passes, you can kick off your model training pipeline. And that's on, let's say, some sort of new data that you're seeing out in the wild. And at the end of that model training pipeline, you're now running a whole set of new tests which are evaluating that model. In the middle of that, there's also a set of, I guess, it's not so much tests as just like validating that the new data that you're seeing and coming in matches some expected pattern. And if it doesn't, then there's probably some sort of update that you need to make to either the data itself or the ingestion mechanism. But yeah, that like there is that conceptual separation between the different sorts of tests. But the reason sort of I started with that 1.0/2.0 analogy is like more framing your machine learning code as just this thing which is writing code for you. And so being part of that same testing pipeline with its own associated tests.
Right. I mean, I think a lot of the value add I bring to the table as a data scientist, it's not so much. I mean, I think software engineers can train a model. It's much more around the model selection process. Like, I really like this idea of integrating tests within a notebook, say, where, so for example, let's just take a really simple statistical analysis, right? Like we want to check whether or not our data is approximately normally distributed, so we can decide whether or not we can run a t-test. That's a test, right? Like that's a validation, but if our data isn't normally distributed, that doesn't mean that we should, you know, fail to push.
Yeah, and I guess I'd see that, yeah, as a form of testing potentially inside EDA or as part of some like structured experiment, which, yeah, as you say, you still want to capture in source control, but is more of that like initial stage of development, which might not go into your test pipeline. And this touches a bit on like the stuff I talked about at the end, which is this whole other area, which is like structured ways of running these sort of experiments. This last dot point here. And like best practices around doing that, using external tools or within notebooks themselves, and then like maintaining things like reproducibility of those experiments that you've run to verify them later, to sort of like audit your model selection choice and things like that. Yeah, there's a whole bunch of topics in there which are really interesting.
Cool, that's a great discussion. They've got quite a few comments here, which I'll just share. So comments on how to test notebooks. So Patrick, we just heard from, says DocTest is a good library. Daniel has recommended Papermill. I'm familiar with that. You can use that to run notebooks and try and test some of the outputs. Daniel also said about who should write the code, that it's a good actually familiarizing yourself with other people's code and functions. Writing tests for that can be a good way. And Anna has said how a machine learning engineer can help with the more complex tests as a data scientist when you're trying to piece it together. So we've got a question from Andrew here. This I think is a good question, Tim. Do you think AutoML and drag and drop feature engineering products will streamline testing or streamline bug creation?
Yeah, good question. So I suppose those sort of products, which Patrick did an excellent talk on last brown bag, are really like the sort of the models that you're using are really well validated and sort of have like quite well understood behavior within the sort of problem space that they're solving. And the same goes for like these out of the box libraries as well. So like TensorFlow used to have all these bugs in it where you could like accidentally set up a neural network that didn't pass information forward, and people would write like unit tests to make sure that like sort of information was actually being passed between the layers of their neural network. And like later on, TensorFlow put out a fix which like ran all those tests themselves. And so I guess you see this like evolving trend of like higher and higher level APIs being open to data scientists to use, which remove some of those implementation details and the associated tests that you would need to write. And AutoML is sort of like the current peak of that paradigm, where just like so much of that implementation detail is now gone for you, and the things that you're really testing are more just like the interfaces between like your model and all the consumption applications around it.
Great. Daniel has also suggested a couple of other libraries. Great Expectations I've just had a quick look at as a data-orientated testing library, a bit similar to, I think it's AssertR in our ecosystem. Yeah, so any other questions, please write them down in the chat. I just have one, Tim, which I think a bit more generally in terms of testing philosophy, and maybe getting some tips from TDD, how to expand the scope of your test. This idea that you can't sort of test for a problem if you haven't thought that it might happen. You sort of think, either data coming in or any parts of your pipeline. You sort of write a test for a specific bug. But if there's a bug that you haven't thought of, or how to sort of get in that mindset of expanding a test, a sort of a series of tests.
Yeah, it's a tricky one. I feel like this is maybe almost like the core problem. And yeah, like this process shown here that I talked about enumerating your happy cases and your sad cases, where you're hypothesizing about the different sorts of things that you might see. Because your production data isn't necessarily going to match your training data, especially as time goes on. And so trying to think about like what those things might look like and how you want your model to behave in those cases, or the rest of your code to behave in those cases when that does happen. But yeah, like, and you're never obviously, like, there's like this very iterative process where you find a bug and then you update it. You're never going to be able to predict everything in advance. But I find like, like going along with some sort of schema like this is the best way that I've found to try and anticipate that stuff. Yeah. Hopefully that helps. And yeah, I guess on the, just to go back to like the notebook tool stuff, something like we're pretty interested in Eliiza in general and have a lot of discussions about is this idea of pulling this whole pipeline and development structure into like a notebook development format. So you're not pulling stuff out of notebooks at any stage. Like obviously tools like Papermill are a way of doing that, and organizations like Netflix seem to be using tools like that and like operating like primarily within notebooks as their IDE. I personally haven't seen like a really good comprehensive end-to-end solution for how you like version control, test, put notebooks in a pipeline, easily extend them, that works. But yeah, I'd love if anyone has any examples of those sort of ecosystems that they can share for them to do that as well. And yeah, I guess we'll close it up. Go ahead, Graham.
questions, yeah, we'll close it up there. So yeah, Tim's email address is there, and we'll send a follow-up. So we've got one last great tool. Daniel's recommended Dagster. This is a great list of tools here from Daniel especially. So yeah, Tim's email address is there. We'll have a follow-up email, as we always do, with the link to the slides. And yeah, get in touch. We look forward to seeing you, or connecting with you in 2 weeks' time for our next Brown Bag. Thanks everyone. Thanks Tim.
Thanks very much. Catch you later.